Welcome to this explainer on the true nature of the rare earth monopoly. Today we're going to unpack a fascinating reality, why the real power in this global industry actually lies far, far beyond the mine itself. In fact, the very device you're using to watch this explainer right now, it relies entirely on the exact monopoly we're about to dissect. We often hear rare earths talked about as a story of rocks in the ground, but by the end of our time today, you're going to see why it's actually a story of extreme industrial leverage.
Okay, let's just dive right in and bust a massive myth off the bat. Earth actually has plenty of rare earth elements. They aren't exceptionally rare in the crust at all. The true monopoly, the real bottleneck that the whole world is waking up to, is the highly complex industrial ecosystem required to process them. We are talking about a fiercely difficult conversion chain from dirt to high-tech components.
So here's our roadmap for today. We'll be hitting the rare earth myth, the systemic conversion chain, light versus heavy elements, the magnet bottleneck, the export control weapon, and lastly, the diversification dilemma. Basically, we're tracking the physical flow of these materials from a wide upstream of raw rocks all the way down to an incredibly narrow downstream bottleneck that, well, practically runs our modern world.
Starting off with Section 1, the rare earth myth. Let's clarify exactly what we mean when we say rare earths, because honestly, the name itself is incredibly misleading.
The defining trait of these 17 elements isn't their scarcity. Actually, they often appear together in the exact same mineral deposits. The core issue is that their chemical properties are so incredibly similar. Pulling them apart from one another requires complex chemical systems, massive capital, and really intense environmental management. It is literally like trying to unbake a cake just to get the original eggs back. It's this extreme difficulty in separation, especially to get the specific elements needed for high-performance magnets, that makes them so strategic.
And the 2025 USGS data brilliantly illustrates this point. Yes, China leads, but mining is completely globally distributed. Even the US and Australia produce significant tonnage. We're talking 51,000 and 29,000 tons respectively. This proves the bottleneck isn't just about who can dig rocks out of the dirt. The US can dig up 51,000 tons of the stuff, but still completely relies on overseas refineries to actually make it usable.
Moving right along to Section 2, the systemic conversion chain. The crucial takeaway here is that real power lies in this chain. Think of it like a river that gets dangerously narrow right at the very end.
To really grasp this, we have to completely shift our mental model from just having mineral potential to possessing industrial capacity. You can't just shovel raw rare earth dirt into a new electric vehicle. You have to mine it, chemically separate it, turn it into metal, alloy it, and then manufacture it into highly specific permanent magnets.
Now, visualize this tightening funnel. Based on International Energy Agency estimates, China controls about 60% of global mining. Okay, but watch what happens as we move down the chain. They control a staggering 91% of refining and an incredible 94% of magnet manufacturing. So the further down the value chain you go, the stronger the monopoly gets.
All right, Section 3, light versus heavy elements. Not all of these elements are created equal, and distinguishing them helps us see where the ultimate choke points for AI and green energy really lie.
We generally divide them into light and heavy rare earths. Light elements, like neodymium and praseodymium, are the core building blocks for standard magnets and are relatively abundant. But contrast those with the heavy elements, like dysprosium and terbium. These are used in much smaller volumes, but they are the absolute magic ingredients that stop magnets from demagnetizing under extreme heat and stress. Electric vehicle motors, the servers running your favorite AI apps, defense systems, they all absolutely need the heavy stuff. And in 2025, the US was 100% reliant on imports for these critical heavy rare earth compounds.
Which brings us to Section 4, the magnet bottleneck. Let's look at the absolute bottom of this funnel. These tiny components act as the throat of green energy and AI data centers.
I really want this number to sink in. 94%. That is China's share of global permanent magnet production. This proves that magnets, not raw oxides, are the real strategic leverage point. The raw oxide is just an ingredient, right? The magnet is the critical industrial component that an automaker actually buys.
And here is why that downstream monopoly is so incredibly sticky. Let's say a wind turbine maker or an EV manufacturer wants to switch to a new magnet supplier. They can't just buy them off a shelf. They have to pass brutal, years-long certification hurdles. We're talking extreme thermal testing, corrosion resistance verification, and compiling literal years of reliability data.
Because think about it, if a magnet fails, the whole motor fails. So once a supplier is locked in, they are incredibly hard to replace.
Section 5. The Export Control Weapon. Now, let's examine what happens when this deeply sticky leverage is actually utilized in the real world through export controls.
Tracking this sequence from 2025 into 2026, we can clearly see how export controls function as structural market realities. In April 2025, China placed export controls on 7 mid to heavy rare earths, the highly strategic ones we just talked about. In October, this expanded to related equipment, though that expansion was later paused to late 2026. However, the April licensing requirements, those remain firmly in place. And this isn't about taking political sides at all. It's just pure market math. Downstream companies are forced to completely reprice what they consider a safe supply.
The stark reality is that supply chain concentration can swiftly become a real-world industrial risk. Even when trade isn't fully banned, the licensing process itself creates a massive barrier. It delays shipments, creates uncertainty, and demands end-use disclosures. It just proves that controlling the bottleneck translates directly to global economic power.
Finally, Section 6, the diversification dilemma. So what will it actually take for Western and allied nations to build an independent supply chain? Can we just dig more mines?
According to the IEEA, $60 billion. That is the staggering investment required over the next decade. And that's just to meet the diversified magnet demand outside of China. It's not a cheap problem to solve because, again, you aren't just opening mines. You have to rebuild the entire industrial ecosystem from scratch. And ultimately, that cost, it's going to be passed down to the consumer, affecting everything from the price of your next car to your household electronics.
And there's a huge systemic challenge to doing this, known in the industry as the co-product trap. Remember how we said these elements appear together? Well, you can't just selectively mine the incredibly valuable high-demand dysprosium. When you dig for it, you also dig up massive amounts of low-value elements like cerium or lanthanum. If the market doesn't want those low-value co-products, your mining project's economics completely fall apart without massive, sustained government backing.
Emphasizing our earlier point, throwing money at rocks just isn't enough. There is a massive metallization gap, the missing middle step of turning raw oxides into usable metal. You need new separation facilities, metallization capabilities to bridge that gap, independent alloy plants, and then you still have to get through that brutal end-to-end customer certification process. The entire stack must be rebuilt.
So, to summarize, from the massive offshore wind turbines turning in the ocean to the precise cooling pumps of hyperscale AI data centers, this tiny volume of material controls massive industrial futures. They are literally the industrial throat of green energy and AI infrastructure. They're the performance amplifiers of the modern age.
I will leave you with this final thought to consider. Given the incredibly tight 94% downstream bottleneck of this supply chain and the billions of dollars in years of certification required to bypass it, are we moving fast enough to secure the hardware infrastructure of our future? It's a $60 billion question we have to answer, and fast. Thanks for joining me on this explainer, and I'll catch you next time.